As we saw in the previous lesson, when we run the simulation, we need to change some of the values to make it run properly. I'm going to go back to the construction mode, and I'm going to start by looking at the rolling joint. When I select that, we can see the X, Y, and Z axis. Upon closer inspection, we can see that the X-axis is the one we're really interested in. That's the force that has to be overcome by the motor. The force times the radius of the small gear will give us the torque, and we can determine if the motor is suitable for this purpose. I'm going to start the motion by going to the standard joints and changing the properties. There are a number of properties we can change in here. I'm looking at the motion. So I'm going to enable motion and change the position. Constant value is not suitable. I'm going to go to a range. Luckily, we only have to change a couple of values here, in fact just one, and that's the ending point. That's negative 270 degrees. Pressing the Tab key shows me the graph of what I've just input. Now I can run the simulation again. And now it's going to look much better. I've given it a range that it can move through, but I still don't have any values. Let's look at it just as a front view. Run the simulation again, going back to the beginning, running the simulation, and the small gear is turning that large gear and the arm. To get the values, I need to go to the output grapher. I'm going to clear any previous settings. And I want to go into the rolling joint and look at the force along the X-axis. And you can see some values already in there. I'm going to run the simulation so you can see where they came from. As the arm goes through that 1 second 270 degree range, those are the values. By clicking on the heading, I can search for the maximum value, which is 13.05. I can now go to the minimum, and we can see where the minimum value occurs. That's at 0 seconds, as you would expect. Let's go back to the max. So why is that point the maximum? Well, if you look at the distance between the pivot point and the distance out to the force, that's where it's at its maximum. Therefore, the maximum force is generated at that point. We can take all of these values and export them in many ways. And as you become more familiar with the simulation, you can try some of these. Keeping that number in mind, we'll need that for our calculation. Just making sure the value is 13.05, and it's definitely pounds force, as you can see when I stretch this out. So closing that down, I'm going back to the construction mode. You can also export this as a movie. You can go out to Inventor Studio, for example. You can also go to what we call finite element analysis and check whether or not the shaft is capable of handling the loads. So you select the time where the maximum load occurs and check the finite element analysis or stress analysis for that piece of material. Let's look at the calculation. Torque equals force times distance. Putting in our values, 13.05 times the radius gives us 3.625 inch-pounds. Using metric numbers, we end up with a value of 0.369 Newton-meters. Comparing those values to the specifications of the motor from the VEX website, we can see that they're well under the stall torque. What else can we do? Well, we can certainly go in and edit the load or the force, perhaps changing it from 2 pounds to 5 pounds. We can also do the workflow in reverse. We can apply the maximum torque to the shaft where the motor is located, then apply an unknown force instead of the 2 or the 5 pound load or force. And that way we can find out the maximum force that the motor can actually raise.